Greetings. It's time for us to begin Newton's law for rigid bodies. So first of all, relative to the Newton's law, this is what you've seen before. The sum of all external forces equals mass times the acceleration for this center of gravity. And we'll note that this is a vector equation, so you could break it down into equation in the x, the y, and the z. All right. But we want to develop some more equations related to rotation. So let's consider one of my ubiquitous blob rigid bodies here. And so this is moving. It can be having translation and also rotation. So we have omega and alpha here. And so here's at some point P in the body, we have a coordinate system, and then this dot is to be the ith particle. So Ri is a vector from this point P that we have to this ith particle, and Fi is the external force on the ith particle. So if we then evaluate this, R cross Fi, so R out to here, then Fi, cross Fi would be the moment of the ith particle upon P. All right? Or we could write it as R cross Ma, because F equals Ma. So we could just substitute in for the force Ma. All right? Now let's suppose AP is known. Then this AI we could say is AP plus alpha cross R minus omega squared R. And we've been working with that equation, so that's not surprising to us. All right? Continuing. So we can take this and we'll substitute it into here. Now, so what you have there is, this is a moment, but we can distribute that moment across. So we can take Ri cross AP, Ri cross alpha cross Ri, and then we have this piece out here. So let's see what those things give us. So moving down a little further, I'll just bring the mass out of the way for now. So I have Ri cross AP. We'll just let that stay. And now here we have, again, I brought the mass out, so I have the mass Ri cross alpha cross Ri. Now let's just note that you have to, whenever you do cross products, you have to do what's inside first. We can't just do this cross this and then add that in. Order matters with cross products. We have to do this piece inside. So here's an eraser. So you can hopefully see this. I'm going to let this thing rotate. So let's assume that that's counterclockwise positive. Okay, and that would be pointing up out of the paper. So out of the paper, cross Ri would produce, for this piece, a vector pointing in the direction of my pen. Okay. Then if you did Ri cross that vector, so you go out with your fingers, wrap, let your thumb point, you get something coming out of the paper again. Same direction as the original alpha. All right, so what is that? You would have, so here's this term just falling down, and this becomes the mass of the eighth particle, R from P to I squared, so that's just the scalar, and then here's our direction and the value of alpha. All right, the last piece was we had an Ri cross Ri. And now this is important. When you do a cross product, if you cross product two vectors that are parallel to each other, you get a zero. So, to say the least, if you cross a vector with itself, it's very, very parallel with itself, so you get a zero. So these terms disappear, so we're just left with this. So now that we have just this term like you see, what's the next step? Well, the particle is the essence of a differential mass. So why don't we call that just a differential mass and then add them all up? That's called taking an integral. So the particle mass, differential mass, all the same thing. And then integrate just as add them all up. So if we add up all of these moments about P, we'd have the sum of the moments about P. Okay, well that's fine. And that would be, so here we have this, we're just going to make M becomes dm and sum them. Acceleration of P is independent from that, so it can be factored out. And then over here, alpha is independent of what's going on here. And so if we look at what we have, this r is from p to every particle. All right, well, what is integral of r squared dm from one point? Oops. Okay, this is nothing more than the mass moment of inertia at point P. That's what it is. All right, and so we've already seen that. That was chapter 10. So now, what can we do with this term? All right, this is a vector integral. So you're integrating the x, the y, and the z, and you're putting a vector out. But the way we've normally seen this is we put in either an x, a y, or a z, and what popped out on the other side was x center, y center, z center. All right. Since it's in vector form, here we're integrating over everything. What we're going to get is r from p to g. So we're going to get all of those dimensions. This is the center of mass equation. So I can replace this piece right here with that. All right. Now, so I can now, inserting that, I can rewrite this equation as the follows. The sum of all the moments about P based on all the external forces is equal to m, r from P to G, so that's going to the center of mass, cross the acceleration at P plus the mass moment of inertia at P times alpha. And given this, we can do something. All right, we can note, if you have pure rotation about P, that would mean the acceleration at P is 0. Okay, so that term would wipe out, and we have this. So this is a special case. But suppose we make P be the center of gravity. Well, r from G to G is 0. That wipes this term out, and we're left with the following equation. The sum of the moments about the center of mass is Ig alpha, and this is always true. It is absolutely always true. Okay? So, we've got this equation. We're still going to do some more work with it. We've got a special case, and we got a very useful equation that's always true. And if we look at that, the sum of the moments about G equals Ig alpha. Wow, doesn't that just look like the same thing? They're basically the same thing. One's generally relative to force, other one relative to torques or moments. All right. So we're going to take this a little bit farther. We're going to take a look at, let's just see, where was that? Right here. We're going to do a little more work with this and see what we can do. And we're also going to do a little work with this. All right. So I'll come back to that actually in just a moment. So let's look at AP for a moment first. And we can express that relative to G. AP is AG plus alpha cross R going from G to P minus omega squared R going from G to P. Again, this is what we were just doing in the last chapter. All right, so we can substitute that in, and we're going to do something else. All right, so we're substituting this piece in for AP, and notice what we did here. Okay, this is using the parallel axis theorem. IP, which is what we had here before, is simply IG plus mr squared, where r goes from G to the point P. So we can break that down. All right, let's keep going. So we got this. Now we're going to have this cross these various parts. So let's start going after that. I have an RPG cross AG. We'll just leave that there for the moment. And then here, I'm going to have an RPG cross alpha cross RGP. So these are negatives of each other. Okay. When I go to do that, I'll leave this to you to do. All right. Just like we did before, I'll just bring this over. We did in here, we looked at alpha cross R, then R cross the result. I'll let you check that out. This works out to be minus m r squared, and whether you put GP or PG in there, it doesn't matter because it's squared. It's just the magnitude. alpha. All right? So that comes out with a negative. This RPG and this is GP. They're in opposite directions, but they're parallel. So this term is basically, other than a sign error difference, this is that cross product with itself. That gives 0. All right, here I just get IG alpha. That's fine. And here I get plus m r squared alpha. And look what we have. Minus that, plus that. So these cancel. So what am I left with? This. The sum of the moments at P is equal to RPG, so this is a vector from P to G, cross mass times acceleration of the center of gravity. Now, at plus the mass moment of inertia times alpha. What I'll note here is if you don't know mass times the acceleration of gravity, this is convenient because it's just basically saying if I know what the acceleration of gravity is, I can use that times mass. Or we could just look at it from the point of view of putting in the sum of all forces. Anytime you have the sum of all forces, you have mass times the acceleration of the center of mass. Okay? So here we have, summarizing, the sum of all the moments at P is equal to R from P to G cross the sum of all the external forces as if they were applied at G. This is a really confusing point for a lot of people because people, what you'd say is, well, you use a bunch of forces and you compute the moment at P. Yeah, and then they'll go, well, isn't this the same thing? We're taking all the forces and going R from P to G, and then the sum of the forces as if they act at G here. And so a lot of people go, well, this and this are the same term. Why do we even have that there? It doesn't even make sense. This is to be 0. And so this is what I want. This is a point where people can get really, really, really confused. And I just want to show how this equation, these two things are different. So how am I going to do that? What I have here is one of my rigid body blobs, and it only has 2 forces on it. So here's a point P and here's a point G, just like we're doing there. All right, I have one force that's vertically above P, and then I have a second force, and that's the only other force that I have is weight, which is coming down on G in the XY plane. So if I take the moments at P, all right, so if we look at the moment of F about P, it'll be A times F, and it's going counterclockwise, so that's positive. And then I have this distance C here, and so the moment of the weight relative to P, that's going clockwise, so that's minus CW. All right, so that's what that equation says. Summing the moments at P is equal to R from P to G, so there'd be a vector here, cross the sum of all the forces, which is equal to MAG. But what that's saying is take all the forces and as if they were applied at G, plus IG alpha. So let's take a look at what this term is. R from P to G, okay, let's do that. Says go over CX minus BY. Here I had in the Y I have A to go from F to P, and then from P down to where G is, there's a distance B. So I have CX minus BY to go to there. Cross the sum of all the forces. I have this force going in the negative X. The weight obviously goes in the negative Y. So I'll do the cross products. All right, I get minus C times the weight in the Z, and this would give us C. Y cross X will give a minus X, and I have 3 minus signs, so that still stays minus. So I get minus B, force F in the Z. Okay, so now, what do we do with that? Note that this equation, the sum of all the moments, lives in the Z plane. So I'm just going to drop the Z's for now. There. And we'll just stick this back in the equation. So here's what I had. The sum of the moments was AF minus CW equals Now I'll stick this piece here is that. Minus CW minus BF. All right, both sides have a minus CW. They can cancel. But this is not equal to that. All right, here we have plus AF. Here I have minus BF plus IG alpha. These, both sides, are different. And that allows you to solve an equation. So the idea that this and that are the same thing, no. This is the moments created based on where the forces are actually applied, taking the moments at P. This says sum all the force, taking the result of summing all the forces and apply them at G. And now take the moment relative to P plus then IG alpha. This and that are very different. All right, so the last thing I'm going to comment on is so we have this really important equation, and so we can now look at special cases. If you have pure translation, that's just Newton's law. The sum of all forces equals ma. If you have pure translation, you have no angular acceleration, so the sum of moments about g is equal to 0. And since there's no angular acceleration, the sum of the moments about p will be equal to rpg cross fg. So they will wind up being equal in that case, if you have no angular acceleration. Whoops. If you have pure rotation about p, Newton's law always applies. The sum of moments about g is IG alpha. That's always true. And we had the special case, the sum of the moments about p is IP alpha. In general, here are your equations of motion relative to Newton. So this is what we want you to use. The sum of the external forces is mass times the acceleration of gravity, of the center of mass. Said that wrong, sorry. The sum of the moments about g is IG alpha. The sum of moments about some other p, and typically because there's good reason to use another p as opposed to g, the geometry will dictate a very natural point to take the moments. Anyway, the sum of moments about p is r from p to g cross what I'll just call fg, which is referenced up here, plus IG alpha. These are the three basic equations. From here you can get everything else. So this is what you want to be able to manipulate, and next time we'll start putting all these equations to work for us. Take care.